Okay, take two. Video number two. Hopefully you cut off the previous video at around 1930. I inverted two of the numbers, so let's try that again, and then we'll try to finish up the other stuff that I wanted to make sure we got through. So, we've got a table, -1, 0, 3, 4, 6, and 10, and you've just got selected y values that go with those, 2, 6, 12, 9, 15, 21. If it helps you, and it might help you because this is the first ever example you've ever done with a table, just draw the thing. So -1 apparently has a height of 2, so there's a dot there. 0 has a height of 6, so there's a dot there. 3 has a height of 12, so that's like, I don't know, there. 4 has a height of 9, and 6 has a height of 15. And finally, you get a 21 if you plug in a 10. So we really don't even know what this curve looks like. We just know a couple of dots. It could go up and down and up, and that's it. Or it could go up, down. In between these things, it could go up and down over and over and over again. We really just don't have any idea. So let's just, for argument's sake, say the curve kind of looks like this. There it is. We just want to find the area under this curve, or I shouldn't say find, I should really say approximate the area under this curve using, in part A, left-hand Riemann sums, and in part B, you eventually want to use just like right-hand Riemann sums. The nice part about the table is they've already broken up the subintervals for you. This is subinterval number 1, number 2, number 3, number 4, and number 5. So the first thing we're going to do is the first little rectangle, if we're doing a left-hand Riemann sum, is going to be there. The base is going to be from 0 to 1, so 1 for the base, and then 2 is the height, because 2 is the left point of that subinterval. Then next, from 0 to 3, the next rectangle is this one. So from 0 to 3, the base is 3, and the height is the left point, which is 6, plus, now we do this one. From 3 to 4, that's 1 unit in space, and the height is 12. Plus, third rectangle is from 4 to 6, so that's a base of 2, and then a height of 9. And then finally, the last one should wind up being from 6 to 10, that's a length of 4, times the height, which is 15. So that just gets you 2 plus 18 plus 12 plus 18 plus 60. 2 and 18 make 20. 32, 42 plus the extra 8 is 50. 50 plus 60 should be 110. Whereas part B, the only real difference is not the base of the rectangles, it's the height of the rectangles. So the bases are all the same. You just wind up using these as your rectangles because you wind up using the right endpoints. And all these purple bars I'm going to kind of get rid of. So the first rectangle still has a base of 1, its just height is the right endpoint, 6, instead of the left endpoint, 2. Second rectangle still has a base of 3. It's just instead of using 6, which was on the left of the second interval, you use 12. Plus, once again, 1, because from 3 to 4 it's 1 unit in space. You just wind up using 9 instead of 12 for the height. Plus, next, you're going from 1 unit in space here to 2 units in space here, times the height there, which is 15. Finally, with a plus 4 times, in this case 21 is the end instead. So you get 6 plus 3 times 12 is 36, plus 9 plus 12 times 15 is 180. Or sorry, 2 times 15, not 12. Sorry, that was a 2, that was a parenthesis. Can't read my own writing. 2 times 15 is 30, plus 4 times 21 is 84. So 84 and 6 make 90. 90 plus 30 is 120. 120 plus an extra 36 and a 9. 36 and 9 make 45, so you should get 165. So, two wildly different approximations, whether you use left endpoints or right endpoints. a big hopeful takeaway here on the table is the bases of the rectangles are not the same. So you can't factor that common number out because your subintervals are of even width. The first rectangle is 1 unit wide, then 3 units wide, then 1 unit wide, then 2 units wide, then 4 units wide. So since you don't have that same number popping up over and over and over again, no factoring, you kind of have to grind through the computation. The nice part is the y-coordinates are just there. You don't have to work them out to figure them out. So it's sort of nicer in one regard and not as nice in the other regard. Last thing about the table, since we don't know anything about the function, we don't know whether it's concave up or concave down, we know it has to increase or decrease at some point in time. It has to do some of both of that. But we don't know concavity, so it's kind of hard to say. We don't really know anything about the function, so we don't know if there are more increasing or decreasing intervals that are not sort of shown from my bad picture, because we just don't know enough to determine overestimate or underestimate. So really just can't ask you that with a table unless you know a little more about the function. So last, we want to sort of talk about just a couple quick other ways and what doing area this way actually kind of means. So you have a nice little, or hopefully if you printed that little handout or if you just have it out, I kind of want to talk about summing things because that's what we're doing here. And there's like a notation that you kind of touch on a little bit in honors pre-calc, but don't do a ton of. So I'd like to just go over the nuts and bolts basics of sigma notation, aka summing stuff, and then talk a little bit deeper about what computing area between the x-axis and using y-coordinates actually means for us. So a couple quick things about sigma notation. The first little example. Whoops, come on top. The first little example says there's a sigma, an n squared, it says n equals 1, and then stops at a 4. What this basically is telling you to do is it's telling you to do 1 squared plus 2 squared plus 3 squared plus 4 squared. You just sub them in. It's basically a sum. That's what the sigma is telling you to do. It's telling you to sum the things. What do? You plug in 1, you square it. Then you plug in 2, then you plug in 3, then you plug in 4. When do you stop? Whatever number's on top. So this is kind of your start, and this is your stop. So we just work it out. We just do what it tells us to do, and we add it. So writing stuff with sigmas allows us to write these sums a little more concisely. Since we're adding up the area of a bunch of rectangles, the sigma notation can make it look a little cleaner, but it also can be a little more confusing if you're not used to it. So if you're ever in doubt, you just grind it out and you just write out all the terms. But this should just be 1 squared plus 2 squared, so 1 plus 4 plus 9 plus 16, so that should be 30. So apparently for this particular thing that I made up as an example, you should get 30. Now, a couple quick things about sigmas and important and useful properties of sums is that if you were trying to find the sum from 1 to 8 of 10 times n squared, this is 10 times 1 squared plus 10 times 2 squared plus 10 times 3 squared plus 10 times 4 squared, eventually stopping at 10 times 8 squared. The thing I'm trying to take away is not really to do this sum. It's kind of tedious. There's more numbers than the one before it, plus there's this extra 10. The key is that all the things are getting multiplied by 10. So if you factor out that 10, you get 1 squared plus 2 squared plus 3 squared plus 4 squared plus etc. You get to 7 squared and 8 squared eventually. So that is just summing all the square stuff. So this is the same thing as 10 times n squared starting at 1 going to 8. So the idea here is that you can take constants and just slide them out through the sigma. Or if you want, I guess you could put this guy in. But ultimately, if you have something like k times the sum of some sequence, let's do it like this. basically constants can essentially just pop through your sigmas. Doesn't really matter what that is. It has to be a constant, though. The n can't go through. N's the variable. N is changing. N starts at 1 and then eventually gets up as big as 8. But constants can pop through your sigmas if you want them to. And that can be kind of a useful thing. The other super important property of sigmas is, or that I want to highlight, is this idea that if you have a series that's a sum of two separate things, so this time I said I equals 1 going to 8 of I squared plus 5i. This time I use the letter I instead of the letter N. No big deal, just a different letter. But I, a lot of people times books and things like that use I for index. But this basically means 1 squared plus 5 times 1, plus 2 squared plus 5 times 2, plus 3 squared plus 5 times 3, etc., 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 until you get to 8. The big takeaway that I'm aiming for here is that it doesn't matter the order you add. So if you want, you could do this as 1 squared plus 2 squared plus 3 squared plus da-da-da-da, stop at 8 squared, plus 5 times 1 plus 5 times 2 plus 5 times 3 plus keep going there. So basically, you can just add up all the squared things first, and then you can add up 5 times all the I second. But if you want, these are the same thing. Since the order you add doesn't matter, you can add up all the squared guys first and then add up all the things. So what it kind of looks like you're doing is it kind of looks like you're distributing the sigma. That's not exactly what you're doing. You're just using a property of sums that says you can do it twice because sigmas just tell you to add and the order you add doesn't matter. So as long as there's a plus sign in between them, you can just do those sums twice. Do them separately and then add them up. And that's kind of a useful thing with sums, is that you can do them separately. Yeah, that's kind of the big takeaways. So the two big takeaways are constants can pull through a sigma, just like an antiderivative. You can take that constant and pull it out. If you're adding, or subtracting really, you can just do those sums separately and do them one at a time and add the totals. Just like antiderivatives, you can take antiderivatives one at a time. Weirdly enough, these are kind of the same idea. The last thing I want to do is get us a formula for the sum of the integers. So what I wrote, and I used an I again on this one, is so I chose the first 100 integers because there's like 100 on top, and now we just kind of have to do it. So this is just 1 plus 2 plus 3 plus 4 plus 99 plus 100. Right, and we're going to work it out. The more numbers you have to add, the more tedious this process is, but there's a really useful, fast shortcut that you hopefully talked about last year in Honors Pre-Calc, that if you kind of write it in this weird sort of different way, that if you pair them in this weird snaking fashion, the first number 1 and the last number 100 makes 101. The second number 2 and the second to last number 99 makes also 101. The third number and the third to last make 101. 101. (52) and 49 make 101. 50 and 51 make 101. That if you group them in this like snaking fashion, you can see that we're going to wind up with 50 pairs of 101. That's pretty much it. So Why do we have 50 pairs? Well, we started with 100 numbers. So each one needs a pair. That's why you have 50 pairs. Or you're going to add up n numbers. So in general, the sum, regardless of where you stop, if you have n numbers, you're going to have n divided by 2 pairs. Where's this 101 coming from? It's coming from the first number, 1, plus the last number, 100, or the second and the second to last, or the third and the third to last. But it's easier to just do first and last. So the first number is 1 plus the second number, or the last number is 100. This is 100 divided by 2 times 1 plus n. N is the last number, 1 is that first number. You might recognize this formula as like n over 2 divided by a sub 1 plus a sub n, because it's just for any arithmetic sequence, it's not that important. What's important is that you know this one, which is how you find the total of the integers. And if you care, 50 times 100 is just like 5,000, so this should be 5,050. But if you want to find the sum of the integers, the key thing is how many integers you're adding, that's n, divided by 2, because that's how many you're grouping them in pairs, and it's whatever the first one is, which is always 1. 1's always the first integer, plus n, which is your last integer. That's pretty much it for sigma notation, quick, super important things to know about summing. So the reason I want to kind of talk about summing is because that's what we were doing in those first examples. We were approximating the area under a curve by finding the area of a bunch of rectangles that sort of fit nicely with that curve. So summing lets you write stuff a lot more concisely. So we're kind of going to segue into how to find area because we need to like adjust our idea. So if you have that document that I am attaching with this file or with this video, we sort of get to this place where there's a big curve, and we want to find the area under that curve. So we want to find this exact area, like all of it. So the game we play is, if we want to find this area with rectangles, we can just, I chose a right-hand Riemann sum, but we can just like find some rectangles that approximate that area and that'll do a good job. But that's an overestimate because a bunch of this stuff on the outside shouldn't be counted. So basically the idea is, what if we make those rectangles even skinnier? If we make those rectangles even skinnier, then you're going to get less area that's creeping out to the outside. If you make them skinnier than that, and skinnier than that, and skinnier than that. So what we basically want to think of is we're going to sort of tweak our area to basically be the area under the curve of a bunch of rectangles. We're going to jam in, you can look at it in two different ways, either jamming in infinity rectangles in that space, or the alternative way to think about it is cram as many rectangles as you can, but the bases of those rectangles is shrinking to 0. So basically what this boils down to is the exact area is a limit. It's a limit of a bunch of infinitely thin rectangles getting jammed under a space. So you, again, can think of it as infinitely many rectangles fitting in that space, but to have more rectangles, you have to shrink their base and make them skinnier. So either think of it as jamming as many rectangles as you can, aka infinity rectangles, or shrinking the rectangles to be as skinny as possible, aka base going to 0. So here's how our new definition is basically going to work. If I want to find the area, say, from A to B, what we did in those first couple Riemann sum examples is we said delta x is b minus a over n. N being how many rectangles do you want to cram in there. So that's what n is representing, the number of rectangles. B minus a is the total space where we're finding those rectangles. So ideally, delta x is going to be the base of all our rectangles. It's just what's the height? Well, the height is dependent on what method you use, whether you use left endpoints or right endpoints or midpoints. In my particular picture that's on this handout that is hopefully something you're looking at, I vote we use right endpoints. So the right endpoint is what happens when we start at A and move over 1 delta x. So the first little rectangle is going to be base, which is delta x, times height, which is f of a plus delta x. The second rectangle is going to be delta x times f of a plus 2 delta x's. We just move over 2 little chunks to get there, plus delta x times f of a plus 3 delta x's, etc., 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 down the line. And we just keep going until eventually we make it to B. The last rectangle is going to come from using B. So what that basically means is officially our new area under a curve, which is really area between the curve and the x-axis, is basically just depends on how many times do you want to add delta x. And that's what the sigma basically can say for us, is that we can just call this f of a plus I delta x's. I basically just is how many times do you want to add delta x. So to get the first rectangle, you want to move from A once. To get the second rectangle, move from A twice. Third rectangle, move from A 3 times, etc., etc., etc. So this is the height. The base is always just going to be your delta x. And then the bottom, you're going to start at 1. And essentially, how many rectangles do you want? Well, that's again what n is. This is officially how we find the area under a curve, like exactly, with one added little tweak. How many rectangles do we want to use? Well, as many as we possibly can. So what we do is we sneak in a little limit, and we're talking about n going to infinity. Ta-da! Infinity rectangles. This is the height of each rectangle. That's the base. So you just start at A, move over 1 delta x to get the first rectangle, 2 delta x's to get the second rectangle, 3 delta x's to get the third rectangle, etc., etc., etc. So that's going to take us to finding the exact area under a curve by sheer will and determination. So what I want to do is find the area under the curve from 0 to 4 of x. So our function is f of x equals x. But we have this new definition for area, which is the limit as n goes to infinity, aka infinity rectangles, n I equals 1 f of a plus delta x times I times delta x. Again, this is just the height, and this is just the base. Now, in a more concise way to write it, we're going to use this symbol that you hopefully are familiar with, and we're going to say that these things are the same thing. This is telling you to find the area from A to B of some function f of x. Because essentially, all this little thing is just a summer. That's why it's like a stretched out s for sum. I've sort of been tiptoeing around this. Now, how this relates to antiderivatives, we'll sort of deal with this. But this symbol is actually different. And the reason that it's different than the antiderivative symbol is there's like an A and a B down here. There's actually letters. So this can be confusing to look at with a bunch of letters and stuff. So let's look at an example that actually has numbers. So our goal is to find the area from 0 to 4 of f of x dx and f of x was just the equation x, aka y equals x, aka this line. So what we're looking to do is find the area from 0 to 4 of this line. So in essence, we're trying to find the area of this triangle, which you hopefully to some extent find to be an absurd process, because you know how to find the area of a triangle. It's just 1/2 base, which is 4, times height, which is 4. I bet we get 8. But this weirder, more complex definition that we kind of talked about is really only good to see if we actually get 8 here. So let's see if we actually get 8 here using our new definition. So if I want to do the area from 0 to 4, first I need to find my delta x. And my delta x is b minus a over n. b is always top number, a is always bottom number, so that's 4 minus 0 over n. So that's just 4 over n. So we say this is the sum of f of a being 0, plus delta x times I times delta x. I starts at 1, ends at n, but n is going to infinity. So this mess of a limit should also wind up being equal to 8. So let's see if it is. So f of x, we actually know what f of x is. F of x is just x. So really, what you should get here is the limit as n goes to infinity, starting at 1, going to n, of, we just plug that in here. So you just get delta x times I times delta x. Except, we actually know what delta x is. Delta x is 4 over n. So we get 4 over n times I times delta x, which is 4 over n. So essentially we get 16 over n squared times I. So far so good, hopefully. So what we're going to do with this is we have to find the sum. Now what's confusing about this is the key is, what is this? And this kind of goes back to those sigma properties I mentioned, I don't know, 10 minutes ago in this video, is that that's a constant. 16 divided by the number of rectangles squared, that guy can pop out of your sigma. So you can take that thing and just throw it on the outside. And I'm kind of being lazy, I almost lost my limit. So we get this. Makes the limit a little easier to do. And then that second thing is, we just talked about how there's a formula for this thing. This guy's formula is n over 2 times n plus 1. And then we have this 16 over n squared. And then we just have to do this limit. So I would recommend, boom, this 16 turns into an 8 if you kill that 2. This n squared and this n should be able to simplify. So we should get 8 divided by n times n plus 1. Toss this guy in. And you wind up just doing the limit as n goes to infinity of 8 over n plus, or times n plus 1. If you toss that in, that's the limit as n goes to infinity of 8 plus 8 over n. That's just officially 8 plus 0, because as n gets really, really big, 8 divided by really, really big is really, really tiny. 8 divided by huge is tiny. 0 plus 8 is 8. So, in the most convoluted, torturous way possible, we have figured out that the area of that triangle is 8, even using our weird, precise definition where we shrink the rectangles down to a size of 0 in terms of their base. So even if we do it long, torturous way, we still get 8. In the future, if you have a triangle, I mean, please just use 1/2 base times height, but I just want to show that our new definition works and does give us the exact answer, because our new definition has some serious, serious consequences, which we're going to sort of focus on our last, I promise this is the end of videos, our last little video. So, let's get to it. So I want to talk about the new consequences of this definition of finding area. We just kind of showed that it worked, and if you have the area of a shape, like a triangle, doing it the long, hard way still gives you 8, like it's supposed to, and that's kind of good. But the consequences of this thing is that, let's say we have a graph, which is on the very, very last page. So I give you a thing that starts at 1, 2, 3, 4, 5, 6. And then sort of looks something like that. So you get a graph that looks sort of something like have a graph that looks like this. So you're asked to find a bunch of different little areas, and the first one is to go from -6 to -2. So I want to find the area under this curve from -6 to 2, aka I want to find the area of this region. Here's -6, here's -2. Essentially, this is just one big long triangle, where this base is 4 and this height is 2. So we can either do it the long way like we did in the previous example, or 1/2 base times height, which is my vote. So if we do 1/2 base 4 times height 2, you should just get that that guy's area is 4. You're welcome to do it the long way. We did it before. That's kind of like torturous and like hard to do. Nothing is surprising yet. Everything is just kind of okay. But the next problem is going from -4 to 1. So for us, that's talking about here's -4, and then here's 1. So we basically have all of this. We basically have this weird shape here. So what I would do is I would just like split it up into a bunch of other smaller shapes. So this shape is here, where that's -2, and that guy's 1. So the base of this little rectangle is 3, and the height of this rectangle is 2. And then if you look at this, you can either call this a trapezoid or split it up into a triangle and a rectangle. But this span goes from -4 to -2. So the base of this rectangle is 2, and the height of this little guy is 1. So this guy is also 1, and this guy is also 2. So that top little triangle is half of 2 times 1. That skinnier, flatter rectangle is 2 times 1. And that big rectangle in the end is 3 times 2. So that's just like 6. So you should wind up getting half of 2 times 1 is 1. That's 2. That's 6. You should get 9 here. That all of this area is 9. Now, do you have to split it the same way I did? Absolutely not. You're just finding the area of some shape. If you know the formula for area of a trapezoid, aka half of base 1 plus base 2 times height, might make it easier, but you can always split a trapezoid up into a triangle or a couple of triangles and a rectangle if that's fine too. But here we get 9. Nothing weird or crazy at all. Everything's kind of fine. So, where do things eventually get weird? Why did I spend so much time talking about that weird alternate way of doing it and those sigmas and those other gross kind of things? It's for things and weird things that happen if we go from 1 to 5. So if you go from 1 to 5, which is all of this green area, we should be doing, it's basically this triangle and then this triangle. if we're going from 1 to 5. So for this triangle, base is 2, height is 2, so 1/2 of 2 times 2. And in this triangle, that's 2. But the height is weirdly -2, because it's down and it's below. So the main thing that I'm trying to sort of highlight from the weird alternate definition is we just use the y-coordinate for the height of the rectangle. But the weird thing is that rectangles can't have, or in general, area can't be negative. But y-coordinates can be negative. But since our definition essentially just says, hey, use the y-coordinate, basically what this means is we can get negative area, which is sort of a strange construct. So here, this area, which is 4, is the same as this area, which is 4, but since this guy is upside down, you wind up subtracting those things and you just get a value of 0. Now, is the area of that space 0? No. The area of that space is like 4 and then 4 again. The area of that space is 8. Sorry, I never cut it in half. So it's half of 4. So it's technically 2 minus 2, not 4 minus 4, but whatever. So ultimately, the area of that space is 4, but the fact that we use the y-coordinate for the height of our rectangles no matter what has some weird consequences for us. And that consequence is net area. That if you're pushing down, y-coordinates are negative. You don't turn them positive. Just leave them as negative. That's fine. So what it boils down to is we kind of shouldn't use the word area. It's more like it's net area. But even that's a little more confusing. So the technical term we're going to use here, when you have what looks like an antiderivative symbol, but there are numbers up here, that the buzzword is actually, that is an integral. And integrals have a definition that is based on area, but integrals themselves are not area, because area can't be negative. So when you find the area of these shapes, if it's facing up, height is positive. If it's facing down, the height is negative, and you just have to make that small little change, and then it's fine. But we're not really finding area. We're doing this thing that has an area-based definition, but since we blindly use the y-coordinate to be the height of every rectangle, we wind up getting potentially negative values or 0 or something like that. So one last weird little example, and then we're all done, and that's just going from 2 to 7. So going from 2 to 7 means we're talking about, here's 2, 3, 4, 5, 6, 7. So we're doing this one, and this one, and then this one. We're going from 2 all the way to 7. So that for you should be this first little baby triangle, which is 1, 1, so half of 1 times 1. If we're trying to do the integral now is the buzz phrase, not the area, from 2 to 7, f of x dx should be that first small little green triangle, followed by this big upside down triangle, which has a base of 1, 2, 3, and a height of -2. So that's half of 3 times -2. And then finally another right side up triangle that's 1 by 2. So half of 1 times 2. Let's just do it. That's a half. That's a whole. Half of 3 times 2 is half of 6. So half of 6 is 3. So that's actually just going to be negative. So it's a half minus 3 plus 1. So this should be 1.5 minus 3. For the first time ever, you have negative area, which conceptually doesn't make a lot of sense. But what we want is change. And you'll sort of see why we are kind of okay with having negative area and the ramifications and why it's actually a good thing. But area itself cannot be negative. But we're doing a definition for a new process that is based on area. But since that process blindly just always used the y-coordinate as the height, that has a consequence. And that consequence is that area can be negative. So we probably just shouldn't use the word area. So we might as well start using this vocab right now. The term is integral. This is the integral from 2 to 7. And integrating is just basically finding the area. You're just assigning it to be positive when it's above the axis and negative when it's below the x-axis. So that's pretty much it for video series number 1. I should be available in office hours in some form tomorrow and Wednesday, but I'll post some stuff on Google Classroom and you should see what's up. So hopefully this worked out okay. We're just testing it out, doing the best we can. I will hopefully see most of you tomorrow or the next day. Thanks. Bye.